Today we're going to start looking at collisions, which we'll be dealing with for the next several days. When two objects collide with each other, we consider them to be a system. We can also say that the forces they exert on each other typically are going to be large compared to other forces acting during the collision. Therefore, we can say that the external force on this two-object system is negligible. And if the net external force is negligible, that means the net external force is approximately equal to 0. Therefore, momentum will be conserved. For a two-object system, we can write this m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. All right, so this is what we're going to be using. And this generalizes, if you added more terms, you could write a three-object collision or four-object collision or whatever. But we're only going to be dealing with two-object collisions in this class. All right, so let's look at this example. Cue ball hits the 8 ball straight on, and the cue ball comes to rest. Cue ball has slightly less mass than the 8 ball. How does the speed of the 8 ball after the collision compare to the speed of the cue before the collision? Well, since it's a collision, say initial momentum equals final momentum, right? Well, initially, oh, I didn't say this. I should have specified in the problem that the 8 ball is initially at rest. I should have included that in the problem statement. Sorry about that. And the cue ball comes to rest. The cue ball has slightly less mass than the 8 ball. So initially, the 8 ball is at rest. So initially, we just have momentum for the cue ball. And after the collision, well, we say the cue ball comes to rest. So we only have momentum for the 8 ball. So if those two things are equal, mass times velocity is equal to the two of them. So bigger mass means smaller velocity. When momentum is equal, so speed of the cue is going to be larger than the speed of the 8. Here's an example of that. In collision, we got a volleyball with mass 422 grams. It's rolling at 2.2 meters per second. Strikes a basketball of mass 624 grams. That is initially at rest. Sorry. That is initially at rest. What is the speed of the basketball after the collision? So initially the volleyball is moving. Final, the basketball is moving. So our initial momentum is mass of the volleyball times velocity of the volleyball. Our final is mass of the basketball times velocity of the basketball. So we can plug numbers in to figure this out. If we're solving for velocities, these values are given in grams. Normally we convert to kilograms, but in this case we've got grams over here, so when we solve for velocity, we can divide and cancel out, so we'll just be left with a velocity in meters per second anyway. You may convert to kilograms if you like, but it's not entirely necessary. If we calculate that out, we get the velocity of the basketball is about 1.5. Oh, sorry, all these had 3 sig figs. So that would be 1.49 meters per second. And it asks for speed. So we don't need to worry about a direction. Speed is a magnitude. There's another example. We've got a car with mass 1,200 kilograms. It's moving at 8.5 meters per second north. When it hits a stopped van with mass 2,200 kilograms, the two vehicles stick together after the collision. What is their velocity? Initially, on the initial side, we've got mass of the car initial times velocity. Well, the car mass isn't going to change. Mass times velocity of the car initial. The van is stopped initially, so it's at rest. And after the collision, they stick together. So this means that they're moving together, which then means that the mass that's moving is the total mass of the car plus mass of the van times the final velocity of the two of them. And then we can plug numbers in and calculate. the final velocity of the combination of the two vehicles, which comes out to 3. How about that? 3.0 meters per second. It's in the same direction as the initial velocity, so that's going to be north. All right, continuing on. A bullet with mass 52 grams moving at 930 meters per second. This is the bullet that we talked about on the first day. When it strikes a target dummy that is at rest, dummy has mass 75 kilograms. The bullet gets stuck in the dummy. So we want to know what is the dummy's speed after the collision. Well, initially, we've got a bullet that's moving and a dummy that's at rest, so only the bullet has momentum. And afterward, we've got a bullet and a dummy moving together. Mass of the bullet. Now here we have grams and kilograms, so we do need to convert one of those. I'll convert the mass of the bullet. Plugging in the mass of the bullet here doesn't really make much of a difference, but we'll do it anyway. Like that, so we can punch this in and figure this out. 930 minus 0.052 times plus 75. And we get a final velocity of about 0.64 meters per second. And I give this example because in movies a lot of times when somebody gets shot, they will go flying across the room. This is the biggest, fastest bullet I could find, 52 grams, 930 meters per second, meaning it has more momentum than any other bullet, just about any other bullet out there. And this would give a stationary target a backward velocity of 0.64 meters per second, less than 1 meter per second. So the whole flying backward across the room, not at all realistic. Movie physics typically does not correspond to real physics. Here's another problem. We got two air hockey pucks striking each other head-on. Puck A has mass 22 grams and is moving at 2.3 meters per second south, while Puck B, mass 18 grams, was initially at rest. After the collision, Puck A continues south at 0.55 meters per second. What's Puck B's velocity? Well, we've got A moving initially, and in the final, we have both moving, and we can calculate. The mass is going to cancel out. 2.3 south, usually we call south negative and north positive, but you could flip that if you wanted to. It would just you would need to keep that in mind when you're finding the answer. And so we'll see what we get here. 22 times negative 2.3 plus 22 times 0.55 divided by 18. Turns out velocity B final is about, so negative 2.13, so negative, so that's about 2.1 meters per second. South. How much momentum was transferred from one to the other? Well, the momentum transfer is how much the momentum changed. So we could see, what is the change in momentum of object B? Well, that's going to be mass of B times velocity B final minus mass of B times velocity B initial, which is 0. So how much momentum transferred is just mass of B. And we want, since we're finding momentum, we want that in standard units, so we should go ahead and convert this mass to kilograms, 0.018. Negative 2.13, use the whole decimal, meters per second, whatever, I don't need that there, times 0.018. So the change in momentum, how much momentum? That's a magnitude. So the magnitude of your change in momentum is about 0.039 with sig figs, kilogram meters per second. So this is momentum that initially the Puck A had the momentum and then it was passed off to Puck B. So total momentum is conserved, but momentum is transferred from one object to another in the course of a collision. Here's another example. In this case, both balls are moving. So we have mass of A, velocity A initial, plus mass of B, velocity B initial. equals mass of A, velocity of A final, plus mass of B, velocity of B final, and we've got numbers for all this stuff. We can go 152, negative 3.5, plus mass B, 145 times 2.8, equals mass of A, which is 152, negative 0.12, plus mass of B, B final, and we can calculate 152 times negative 3.5 plus 145 times 2.8 plus, moving this over, 152 times 0.12, add all those up, divide by 145, and so B final comes out to negative 1.0, so that's 1.0 meters per second south. So a more conceptual question. Got a car with mass m and a truck with mass 3m. They collide. Which vehicle had a greater change in momentum? Well, in a collision, momentum is conserved. So momentum of the car plus momentum of the truck initial equals momentum of the car plus momentum of the truck final, which means that any momentum that was lost by the truck was given to the car, or vice versa. So change in momentum of the car must be equal and opposite to change in momentum of the truck. So neither has a greater change in momentum. Which vehicle has a greater change in speed? That would be the car. Change in momentum of the car equals change in momentum of the truck. If we take absolute values. So m delta v of the car is equal to m delta v of the truck, absolute value. So if we know the mass of the car is less than the mass of the truck, so change in velocity of the car is greater than change in velocity of the truck. And we could infer from the ratio of the masses that the change in velocity of the car is in fact 3 times larger. I alluded to this. Is the momentum of an individual object conserved in a collision? No. Momentum of the system is conserved. Individual objects will transfer momentum from one to the other.